Hello, dear students. I am Samir Velankar. I welcome all of you to this second video on Bellman Ford algorithm. In the first video, we saw an example graph and we solved the problem of finding shortest distance from source S to all other vertices. We also know a term called relaxing an edge, and the relaxing of all the edges was done v minus 1 times, where v are the number of vertices. Now, in this video, I'll tell you some problem which is associated with Bellman-Ford's algorithm. Bellman-Ford's algorithm can actually, check, that's an advantage actually. It can check whether there are any negative weight cycles in the graph. So you please try to first understand what the term is negative weight cycle. Now observe the graph shown below over here, and you watch that there is a cycle existing in this graph as follows: 2 to 1, then 1 to 3, and 3 to 2 again. So the cycle is 2 to 1, 1 to 3, 3 back to 2. But the weights of 2 to 1 is minus 6. As you see, added with, if you add all these weights, weight from 1 to 3 is 3, and weight from 3 to 2 is 2. If you add the weights which comes in the cycle, the addition will come out to be minus 1. Now, if you have a cycle in the graph and the addition of all the weights in that cycle comes out as negative, some negative quantity, then such a cycle is called negative weight cycle. And listen carefully, if there exists a negative weight cycle anywhere in the graph, then Bellman Ford algorithm cannot find single source shortest distance. Or rather, the Bellman Ford algorithm announces that it cannot find the answer because the graph has a negative weight cycle. I hope you have understood the negative weight cycle. As another example, just imagine that we have some vertices as follows: P, P to Q, Q to R, and R back to P. So clearly this is a cycle, and P to Q is 3, whereas Q to R is 1, and we have R to P as minus 5. Now in this cycle, if you add all these weights, 3 plus 1 plus minus 5, you will get the sum of minus 1, isn't it? Or let's say if the weight of Q to R was 1, but the weight between P to R was minus 6, then the sum of all the weights will be 3, 1, and minus 6, which will be equal to minus 2. So the sum comes out as negative. So we say this is a cycle whose addition of all the weights comes out as negative, and such a cycle is known as negative weight cycle. Just imagine for some time that weight between Q to R, just imagine, was 4. In that case, the addition of all the weights will be 3 plus 4 minus 6, which will come out to be positive 1. Now, such a cycle is not a negative weight cycle. I hope you understood what is the notation of negative weight cycle. Now, if such a negative weight cycle exists, then Bellman Ford algorithm will fail to find out shortest distance. Let's find out shortest distance from 0. This is our source vertex, assume 0 to all other vertices. Now check that there are 4 vertices, V is 4, and the number of edges E over here is 1, 2, 3, 4, 5. 5 edges are there. So what we have to do is we have to relax all the 5 edges, correct? V minus 1 times. That is, we have to relax it 3 times. Okay? So let's try solving this example. So what we are going to do is Here, all I have explained, you can pause the video and check for this text. Some definitions I have given of negative weight cycle and all that. But let's solve Bellman Ford algorithm for the above graph. How are you going to start? You know the procedure now. Whatever is the source vertex, you know, will be at distance of 0, and all other vertices will be at distance of infinity. And we will relax each and every edge now. So I have written list of edges again over here. Let's start. Now let's start with the 0, 1 edge, which I am striking out here. Now 0 to 1 edge, if you relax, you will have to add 0 with 5. I'm not explaining all the procedure about relaxing the edge, but the sum comes out as 5. So distance of first vertex is at infinity and we got a lesser distance, so we'll update distance of first vertex to 5. 0, 2, if you take this edge 0, 2, then 0, 2 you observe will be relaxed by using 0 plus 4, which comes out as 4, and distance of second vertex is right now at infinity. We got a lesser distance, we'll update it to 4. 2 to 1, next edge I am taking. 2 to 1 you observe is now 4, distance of second vertex 4 plus minus 6, which comes out as minus 2, and distance of first vertex is 5 you observe, and minus 2 is much lesser, so we'll update this. 1 comma 3 I am relaxing. The edge from 1 comma 3 will be relaxed by using a rule minus 2 plus 3, which is 1. So distance of third vertex is no more infinity, it is 1. And finally 3 comma 2, if you relax 3 comma 2 edge, this edge, it will be 1 plus 2, correct? Distance of third vertex plus cost of 3 comma 2, which is 3. And you observe vertex 2 is at distance of 4 and we got lesser distance 3. So after relaxing all the edges for the first time, the vertices 0, 1, 2, 3. These are the vertices are at distances 0, minus 2, then second vertex is at 3, and third vertex is at 1. That has been written below over here. Distances of all the vertices have been written, and the refreshed graph has been shown here with the new distances. But this was just the first cycle. And remember, we have to do this 3 times because there are 4 edges, sorry, 4 vertices. Let's now relax all the edges again with the new distances. Let's try to relax 0, 1. Now 0, 1, while relaxing this edge 0, 1, you will do 0 plus 5, which is 5. But first vertex is already at distance minus 2, which is much lesser than 5. So you won't update distance of first vertex. 0, 2 you observe, 0, 2 will be this time 0 plus 4, which is 4. But second vertex you see is already at distance 3, which is less than 4. So you won't update distance of second vertex. Let's relax edge 2, 1. Now if you relax the edge 2, 1, there is something interesting. You watch. While relaxing this edge 2, 1, the sum of 3 plus minus 6 comes out as minus 3, correct? It comes out as minus 3, and vertex 1 is right now at distance minus 2. Listen, we got a lesser distance minus 3. Minus 3 is less than minus 2. So vertex 1 gets updated to minus 3. Let's take the next edge 1, 3. Now 1, 3 is again interesting, you watch. This edge 1, 3 will be relaxed by using minus 3 plus 3, isn't it? Which is 0. And third vertex right now it has 1. So it gets updated to lesser distance 0. Finally 3, 2. This edge which I am marking 3, 2 will be 0 plus 2, which is 2. But vertex 2 is right now at larger distance 3. So it gets updated to 2. So after relaxing all the edges for the second time, these were the edges 0, 1, 2, 3. The distances of all these edges are 0, minus 3. Second vertex is at distance of 2 and third vertex is at distance of 0. So that is what I have written over here. The distances of all vertices are 0, minus 3, 2 and 0. So I have shown the refreshed graph after the second updation. These are the new distances. But now we have to relax all these edges for the third time. Because there are 4 vertices, we have to do it 3 times. So let's relax 0, comma 1. 0, comma 1, there is no change because this is 0 plus 5, which is greater than minus 3. Vertex 1 is already at distance minus 3, isn't it? 0, comma 2. 0, comma 2, this edge will be 0 plus 4, which is larger than 2. So vertex 2 is already at lesser distance, 2, comma 1. Now observe this 2, comma 1 is 2 minus 6, isn't it? 2 and minus 6, which is minus 4. So you observe this vertex 1 is further reducing its distance, isn't it? Now 1, comma 3, observe 1, comma 3. This 1, comma 3 edge will be minus 4 plus 3, which is minus 1. So vertex 3 will get updated from 0 to minus 1. We got lesser distance. And finally 3, comma 2, the last edge, 3, comma 2 will be minus 1 plus 2, which will be 1. And you observe vertex 2 is at distance of 2. It has got lesser distance now, which is 1. So after updating all the vertices 0, 1, 2, 3 for the third time, we got the distances as 0, vertex 1 is at minus 4, vertex 2 is at 1, and vertex 3 is at minus 1. That is exactly what I have written over here. Distances are 0, minus 4, 1, and minus 1. So I have shown the refreshed graph with the new distances. Now, actually, Bellman Ford algorithm should give the answer after 3 updations. I hope you are understanding why we are updating all the edges or relaxing the edges exactly v minus 1 time. Now, listen, if there are 4 vertices in our graph, just imagine, then what can be the longest path from source S to any vertex? The longest path, can be 3. 1, 2, 3. That means if you want to find out the longest path which is reachable from S to any other vertex, it can be of the size or of the path can be of the length v minus 1. So by processing the graph or processing all the edges v minus 1 times, we ensure that now definitely we should get the answer. But here is the twist now. We have updated all the edges, relaxed all the edges 3 times. But let's try to relax all the edges once again. So with this latest distances, I'm going to update all these distances again. I relax all the edges. Let's try 0, comma 1, the first edge. 0, comma 1 relaxation will be done by adding 0 and 5, which doesn't affect minus 4. This is much less than 5. Then 0, comma 2. 0, comma 2 is also not going to affect anything because 0 plus 4, correct? 0 plus 4 is 4, but vertex 2 is already at distance 1. 2, comma 1. Now, when you watch 2, comma 1, something interesting you see. It is 1 minus 6, which is minus 5, but vertex 1 is at minus 4 and we have got lesser distance. Now, this is surprising. Even after relaxing all the edges 3 times, which we have already done, and we are now relaxing all the edges for the 4th time, even then the distances are changing. That means there is a negative weight cycle, and this will continue if you even if you relax the edges 5th time, 6th time, 7th time, infinite times. These distances will keep changing and we will never come to a stable solution. Let's continue. Let's do 1 comma 3, the next edge. 1 comma 3 will be relaxed by using minus 5 plus 3, which is minus 2, and vertex 3 is at minus 1, so it gets updated to minus 2. And finally 3 comma 2, 3 comma 2 you observe will be relaxed by using minus 2 plus 2, which is 0, and vertex 2 is at distance of 1, so it will get updated to 0. That means the distances are changing even after updating or relaxing all the edges v minus 1 times. If we continue, the distances are changing. Then Bellman Ford algorithm announces that the graph has a negative weight cycle and we cannot find, that's the answer, we cannot find shortest distance. Here we go. That's what I have written, the updated Updated distances have been written after the fourth repetition, and we have got the changes in the distance. So hence we cannot find shortest distance because there exists a negative weight cycle. That's what Bellman Ford algorithm is all about. In summary, Bellman Ford algorithm will definitely find out shortest distance from given source to all the destinations. But after v minus 1 repetitions, if there is change in the distance, when we update relax all the edges after v minus 1 times, if there is any change in the distance, then Bellman Ford algorithm will announce it cannot find shortest distance. Now before I end this video, let's talk about time complexity of Bellman Ford algorithm. Now time complexity is very simple. Just check, we are doing something for v minus 1 times, we are doing some procedure, isn't it? What procedure? We are doing this relax all e edges. Now you watch, relaxing of all e edges is done v minus 1 times. That means if you imagine that the time taken for relaxing all the e edges is big O of e. Imagine for relaxing one edge, you require 1 unit of time. Then relaxing all the e edges, you will need e units of time. So if you imagine this is OE, then this OE is repeated v minus 1 times. If you just imagine this is v times for some time, because minus 1 is not going to affect much, then or else what you can do is you can say that okay, OE is repeated how many times? V minus 1 times. So this is nothing but O of V minus 1 multiplied by this. So ultimately, we are going to get E into V minus 1, isn't it? So basically, you can write this as order of E, number of edges into number of vertices, isn't it? I have removed that minus 1 as it is polynomial of degree 1, V raised to 1 minus 1, and this is E raised to 1. So we can write number of edges into number of vertices is what the big O is, the big O of Bellman Ford. But many times, you might have a complete graph or rather a dense graph. Now if you have a complete graph, just check this. In a complete graph, there is an edge from every vertex to every other vertex. In that case, number of edges is v into v minus 1 by 2. This is a rule about complete graph. As an example, if we have, let's say, if we have 4 vertices and there is an edge from every vertex to every other vertex like this. So this is a dense graph, isn't it so? This is a dense graph. And number of edges in this graph, we will have edge from this vertex to this vertex also. Very messy, but you just imagine there is a edge from every vertex to every other vertex. This is a complete graph. Then number of edges in this graph will be 4 into 4 minus 1 upon 2. That will be 12 upon 2, that is 6. Now you watch, these are the number of edges in a complete graph. So, and height is that in a complete graph there are lot of edges, isn't it? And we have to relax all the edges v minus 1 times. So in that case, if we have a complete graph, then you know that Bellman Ford works in the order of or in the big O of E, V, number of edges and number of vertices, but number of edges in a complete graph is v into v minus 1 by 2. So this comes out as v square minus 1, sorry, minus v upon 2. So if you leave out this minus v and upon 2, as you know, this is a polynomial of degree 2, what we are going to now get is this formula, or this big O notation becomes O v square into v. Just check, this number of edges can be approximated as v square. Actually, it is v square minus v upon 2, but we are writing big O notation. So we can remove these smaller terms and we can write the degree, that is v square, and it comes out as O v cube. So remember, Bellman Ford algorithm in the worst case, this is the worst case, when we have a complete graph, when there is dense graph, when there are lots and lots of edges in the graph, then it works in the big O of V cube. V are the number of vertices. But if we have sparse graph, then this is the best case, isn't it? We can say, or average case also. It works in big O of number of edges into number of vertices. That's it for Bellman Ford algorithm. Thank you very much.